Hi guys, and welcome back to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kiriakou, and right now we're just going to continue on looking at geometrical properties of cross-sections of beams. So in the last video we actually took a look at the first moment of area. So the first moment of area, and that was this, we looked at the centroid and how to calculate the centroid of a simple geometry and also of a composite area. Okay, so if I had a beam and I had a cross-sectional area, it was either going to be like a simple geometry, like a rectangle, or we were going to have something like a T-bar where we could find where the centroid is, and passing through the centroid was the neutral axis. So now we're going to take this one step further and actually be able to calculate the moment of inertia, which is the resistance to bending. Okay, and we can also describe this as the second moment of area. Okay, so let's just take a quick look at why we need to be able to calculate the resistance to bending. And this actually goes back to what we were looking at earlier of the flexural formula. So being able to calculate the stress in a beam, and it's actually the bending stress, where we have sigma equals minus my on I, and we said that this was our section modulus, and this is actually what determines, this is based on the cross-sectional area of the beam. So today we're going to look at how to calculate I, moment of inertia. So let's just clean this up. Okay, so let's take a look at a beam. So if we have a beam, and it looks like this, and I have, this is the thin section here is the cross-sectional area of my beam. Depending on the orientation of this beam, my moment of inertia, my centroid, is going to be different. Okay, so which way? So the other way actually I can orientate it is like this. See if I can draw this properly. So this cross section is going to be along here. So I can actually orientate the beam into different ways. So if I have a load here, and I have a load on this surface, so I'm carrying this surface here, which orientation is actually going to be stronger? So this one here is actually going to be a stiffer orientation because we have a narrower cross-sectional area where the beam is, where the load is being applied. Okay, so this material is going to be, this orientation is going to be stiffer. So even though the cross-sectional area of the beam is the same, why is it that in one orientation it's going to be stiffer to the other? So let's just take a look. So if I have my neutral axis along here, and the cross-section of the beam looks like this, that one, and for this one it's going to look like here. So, it's my neutral axis. So, we are bending about this point. What's going to happen? The further away the material is from the bending axis, okay, so we can call this bending axis. So the further away the material is, okay, the higher the stress is going to be, the further away the stress will be from the neutral axis. Because remember here we said that sigma equals 0, okay, on the neutral axis. So the further we go from this neutral axis, the higher the stress. So we have more material occurring away from the neutral axis compared to this distance. So if we had a material cross-section like an I-beam, let's take a look at that. And this is why. So I'm just going to draw it here. So here's my neutral axis. And here I have an I-beam. This is my cross-sectional area. So, if I take a look, here, the majority of my material is further away from the neutral axis. And this is why. So, this is going to be more resistant to bending. So, this is why you see I-beams in a lot of constructions, because it's very strong, stiff material, cross-section, I should say. So, let's take a look at how to calculate the moment of inertia. Okay, so to calculate moment of inertia, we're going to need to know where the centroid is. So if I have just simple geometry, so if I have just a rectangle, and here is the centre, my centroid, and this is B, and that's H, and here is my axes, X and Y, for my centroid. The moment of inertia I, and this is found in any textbook, in the X is going to be 1 on 12 BH cubed. And in the Y, if we rotate around the Y-axis, it's going to be 1 on 12 HB cubed. So in this class we're going to be pretty much looking at rectangles, so areas, so rectangular cross-sectional areas, and circular. So if I have a circle, and here is my centroid, and I have, let's see, I have Y and X, it's just simply going to be, IX is going to be 1 on 4 pi R4, so we have a radius, and it's going to be the same thing in the Y. So really what we're going to look at now is different orientations and how to calculate composite areas for the moment of inertia. So there's a couple of tricks that we can do. If we have simple geometry like this going on, and as long as the centroids are in the same location, I can calculate moment of inertia quite easily. Let's take a look. Okay, so if I have a plate with a hole in the centre, and this is going to be H, this is B, and I have a radius R. So if the centroid of the circle, so actually I won't write it there. So if the centroid of the circle and rectangle are the same, I can simply subtract the two moment of inertias. Here's my Y and my X. So I can actually break that down into the moment of inertia of the rectangle. That's B and that's H, minus the whole moment of inertia of the circle. So IX, we know that that is 1 on 12 BH cubed minus the moment of inertia for a circle is 1 on 4 pi R4. So I simply have this equation. But not everything is going to be this simple. Like if I want to calculate the moment of inertia of a T-bar, how am I going to do that? So let's take a look at how to calculate the moment of inertia for a composite area. composite area where we have, say, T-bar. I'm going to have two geometries. Yeah? I can break it up into two simple objects. So how do I calculate this? Here will have a centroid of its own, this one will have a centroid, and the whole geometry will have a centroid at x bar, y bar. And my neutral axes will pass through the centroid. So this is what we learnt how to calculate in the last video. But now how do I calculate the moment of inertia of a composite area? So if I just take a look at just a simple rectangle to start with. Here's my rectangle, here's my centroid. That's my neutral axis, or my x-axis here, and label it as. If I want to now rotate about a different axis, so if I move my axis up here, so now it becomes x bar, I have to compensate for this distance. Yeah? So I can use the parallel axis theorem to do that. So I'll have Ix bar, so my moment of inertia about here, it's going to equal Ix plus AD squared. So this is the component that compensates for the shift in the x-axis. But this only occurs if these two lines are parallel. Okay. So we can apply this theorem to find out what the moment of inertia is for the I-beam, the T-bar. So let's take a look. So, if this is for just one shape, if I have multiple shapes, then I need to actually put in the sum. Because I'll need to add in, and I'll have an I in there. Because I need to add these geometries. So, let's just take this apart and have a look at it. I'll rewrite the equation up at the top. So here I'm going to use the parallel axis theorem. So this is going to be equal to saying I'm going to keep this axis going along here, my neutral axis, and I'm going to break each geometry up. So here I have the top rectangle, and here it's going to have its own centroid, call it C2. So we know that this is going to have a distance, we could call that B1, and we can call this, actually we'll call it 2 since it's number 2, and we can call this H2, it's got a height. So this is my neutral axis. When we're looking at the equation for the parallel axis theorem, we have I dash equals the sum of Ix plus sum of AID squared. Yeah? So we need to be able to find D. and D is going to be the distance from the neutral axis to the centroid of the individual geometry. So we can call that D2. And we know what the area is, because we can calculate that area. The area is going to be B2H2. So I can write here that I've got this equation. So I have 1 on 12 B2H2 cubed plus my area, so B2H2, and my distance is D2 squared. So this is I x bar 2. So to find this geometry, what are we going to do? We're going to draw that and draw here. So this is where the centroid sits, so x bar, y bar. And here is where C1 sits, the centre of my, the centre of this geometry. So, what's the distance going to be? It's going to be from the neutral axis to the centre. That's going to be D1. So for this, I'm going to have, we can call that B1, and we'll call that H1. And my area is going to be B1H1. And I can say that I can calculate I x1 bar. So we're just going to add these two up here and put a plus there. So 1 on 12, B1H1 cubed plus the area is B1H1 and my distance is D1 squared. So I can calculate, if I add those two up, I'm going to have this. So that's how you calculate the moment of inertia of a composite area. There are lots of examples in the tutorial problems, so take a look at those questions. And I'll see you in the next video.